Good day, everyone. My name is Jaybie Guzman from the University of the Philippines, Diliman. Today, I'm going to talk about our work on unraveling spatial privacy risks of mobile mixed reality data. So this is in collaboration with Dr. Kanchana Thilakarathna of the University of Sydney and also Professor Aruna Seneviratne of the University of New South Wales, also in Sydney, Australia. So, following the popularity of the augmented reality game Pokemon Go, so mobile platforms have soon launched their own augmented reality SDKs and APIs. For example, Apple has launched the ARKit, and also Google has launched the ARCore for the Android. And here are some examples of how they envisioned multiple users can actually interact and collaborate virtually, but on the same physical space. Aside from these software development kits and APIs, so mobile platforms have also improved their sensing capabilities by improving the visual sensors. And aside from these handheld form factors, we also have these head-worn form factors such as the Microsoft HoloLens, which also pushes the developments in the holographic display technologies. Now, given the increasing sensing capabilities as well as the ubiquity of these devices capturing our spaces, we are actually exposing ourselves to potential privacy risks as hackers who have access to these 3D capturing APIs or SDKs. So in an earlier work, we have actually demonstrated these risks as a location inference attack, where the location can be inferred only from the spatial data without access to the location data. Now, in this work, we try to leverage on those same attackers, and then we present a potential spatial measure that can be used as an indicator of spatial privacy risk. That is, we look at whether the inherent structural complexity of a space indicates its spatial privacy risk. So now here are examples of these 3D mixed reality data captures. So here's the actual scene, and then these are captures from the HoloLens, the generalized version of these. And then here are also some of the captures from ARCore. Now, using these 3D data, what an attacker can do is try to use those previous or historical captures as its reference set, and then create a model out of that, and then use that model to inference subsequent spaces that have been exposed from the field. So this is an example. This is our reference attacker. So we used two attackers, the NN matcher and the point of view. So the NN matcher tries to leverage on the local structural information, and then the point of view that uses neural network. Here on the testing set, so we tried to change the size of the revealed or the exposed space, and obviously as we increase the space, we also increase the attacker success. And now let's go to the actual spatial privacy risk indicator. Here we leveraged on this self-similarity shape functions as our potential indicators of risk. So we played around with these three potential measures. So we have a distance-based measure, a normal vector similarity-based measure, and then a neighborhood normal vector similarity-based measure. So the first two are random heuristic, while this one is more of like exact. It has to compute the nearest neighbors, so it's relatively slower than the first two. So I have here the distributions of the shape similarity measures for some example spaces in our dataset. So what these tell us is that for a given space, it has portions that are less similar, hence lower valued, and it also has portions that are more similar and hence are higher valued. So given that those distributions, what we did was use the mean median value of these measures as our threshold, and then use the fraction of these low valued similarity as our chi complexity measure, which then we use as our indicator of risk. That is, a higher chi means that you have a higher spatial privacy risk. So to determine the viability of these metrics as an indicator of risk, we get their correlation with the attack success. Here, what we can see is that the pairwise and neighborhood normal vector similarity-based complexity metrics have high correlation with attack success, while the distance-based metric has a weak correlation, mostly inverse correlation, and hence is not a good indicator of risk. However, we see as well that for a neural network-based attacker point and VLED, it seems that its attack success has no correlation to the complexity measures. So what we can generally take away here is that deep learning-based attackers such as point and VLED is less affected by complexity, which can pose potentially stronger risks. But despite these indicators, despite it being less affected by spatial complexity, we can still say that the normal vector similarity-based complexity measures, both the V2 and then this neighborhood similarity-based, are still good spatial inference risk indicators, especially if the attacker relies on these local information. that is similar to the NN matcher, which relies again to this local structural information. So to conclude this presentation, again, we reiterate that these deep learning neural network-based attackers are potentially less affected by the complexity of the spaces and hence pose stronger privacy risks. And also both the normal vector-based complexity metrics, chi-v2, and the chi-xi are good indicators of spatial privacy risk, but computing chi-v2 is faster. So given that these 3D sensing and vision developments are very fast, and also ensuring and providing spatial data privacy is relatively slower, so having this faster and similar chi-v2 as a potential indicator of risk should be welcome to users to inform them of their spatial privacy risk. So yeah, that's it for this presentation. Thank you very much for listening. So you can reach out to me via this email here, and thank you so much. Bye.